Good day, everyone. Welcome to a new day of learning where we got to learn new things. In this video, we are going to dive into RSA algorithm, which means Rivest Shamir Adelman algorithm, one of the most trusted algorithm in cryptography. We'll explore how RSA works, walk through a real simulation, and assess its performance and limitations. The RSA algorithm, introduced in 1997, is a cryptographic system designed to secure communication over untrusted networks. It ensures confidentiality, authentication, and digital signatures through asymmetric encryption using a public key to encrypt and private key to decrypt, or vice versa. Before we proceed to the simulation, let me discuss first the terms and definition that will be used in this algorithm. First, the term factor. Factors are the numbers you can multiply to get the original number. For example, the factors of 12 are 1, 2, 3, 4, 6, and 12. Since 3 times 4 is equal to 12, as well as 2 times 6 and 1 times 12. Next is the prime numbers. These are numbers whose factor are only 1 and itself. For example, 2, 3, 5, 7, 11, and so on. Next is semi-prime numbers. These are numbers whose factors are prime numbers, such as 21. The factors of 21 are 1, 3, 7, and 21, which are all prime numbers. The last term is modulo. Modulo is just the remainder of a division. For example, 12 modulo 5 is 3, since 13 divided by 5 is 2, and the remainder is 3.
So, hi everyone. The next part of this presentation is the RSA simulation test case 1. So, the first step is we need to generate keys. To make the keys, we need to select two prime numbers. For this simulation, we will use 7 and 19. So, it will be P equals to 7 and Q equals to 19. The second step is to calculate the product of P and Q. So, it will be 7 multiplied by 19 equals to 133. Step 3 is to calculate the totient. To calculate the totient, it will be 7 minus 1 or p minus 1 multiplied by 19 minus 1 or q minus 1. So in this example, the answer will be 108. So our totient will be 108. Step 4 is to select public key. In the simulation, we will use 29 because when choosing a public key, it must be prime. So 29 is prime, must be less than the totient. So 29 is less than the 108 or the totient. And also, it must not be a factor of the totient. Step 5 is to select private key. Also, when deciding to select a private key, we need to follow the formula. Example, product of D or the private key will be 41 and E, which is 29, will be divided by T or the totient 108, and the result must be in a remainder of 1. So the next part, the test case 1, is the encryption and decryption. So the formula for encryption is message raised to the power of E or the public key modulo N equals to ciphertext or the encrypted message. And the formula for description is cipher raised to the power of D or the private key modulo N. And the answer must be equal to the message before encrypted. So next is we will use the formula given earlier. For our example, the message is 60. So we will encrypt it with public key and decrypt it using private key. So for the encryption part, it says in the formula that message raised to the power of public key. So it will be 60 raised to the power of 29 modulo by n, which is 133, And the answer is the ciphertext. The ciphertext will be 86 or the encrypted message. And to check if the algorithm is working or correct or accurate, we will decrypt it using private key. So we will get the ciphertext or the encrypted text, which is 86. We will raise it to the power of 41, which is the private key, modulo by n or the 133. And the answer must be the message or the decrypted message earlier before encrypted. So the next part of our simulation after that example for test case 1 is the test case 2, the digital signatures. This part is we will switch the private key and public key in our formula for encryption and decryption. So now the formula for encryption is message raised to the power of d for the private key modulo n. So the answer will be the ciphertext or the encrypted message. And the formula for decryption is the ciphertext or the encrypted message to the power of E or the public key modulo n. It must be it must be equal to the message before it encrypted. So after we switch the private key and public key in our formula for encryption and decryption, we have example here. So we'll encrypt with private key and decrypt with public key. For encryption, the message will still be 60 for this example. So in encryption, 60 to raised to the power of 41 modulo 133 equals 72. So the ciphertext or the restricted message is 72. So in decryption, the ciphertext or the encrypted message 72 raised to the power of public key or 29 modulo by 133. The result is 60, which is our message. So this proves that our algorithm is still working even we switch the private key and public key in our formula.
RSA time complexity is O of n raised to the power of 4 due to operations like prime generation and modular exponentiation. While it provides strong security, RSA is lower than symmetric encryption algorithm like DES or AES. The encryption and decryption processes involve complex mathematical computation, including exponentiation with very large numbers, which increase in difficulty as the size grows from 1024-bit to 4096-bit keys. Additionally, the generation of large prime numbers, which are essential for key creation, can take significant computational effort. This makes RSA impractical for encrypting large files or real-time data transmission. Instead, it is mainly used for encrypting small pieces of data like keys or hashes in secure communications. Benchmark studies show RSA average throughput is just 2.6 kilobits per second, make it inefficient for large data encryption.
What are the strengths and limitations of RSA algorithms? The strengths are, first, based on the hard problem of factoring large numbers. RSA security is built on the difficulty of factoring a large number that is the product of two primes, called a semi-prime. So while multiplying primes is easy, reversing the process, factoring them back is extremely hard. So this one-way function makes RSA highly secure against brute force attacks. Next is enables encryption, authentication, and digital signatures. RSA is versatile. It lets us encrypt the data for confidentiality, sign messages for authentication, and we verify those signatures to ensure data integrity and non-repudiation. So this makes it useful not just for privacy, but for verifying the identity and legitimacy of settlers. And the last is long-standing trust and real-world deployment. So RSA has been trusted for decades in security protocols like HTTPS, email encryption like TGP, and secure remote access like SSH. It's been tested extensively and stood the test of time, giving it a reputation as one of the most reliable cryptographic algorithms in history. Now, let's proceed to the limitations. The limitations are first, computationally expensive. RSA is slow. Its encryption and decryption involve heavy mathematical operations like modular experimentation with a very large numbers. So this makes it unsuitable for encrypting large files or data streams in real time. It's why RSA is usually combined with faster symmetric ciphers like AES. Second is vulnerable to future quantum computing via Shor's algorithm. Right now, RSA is safe, but if large-scale quantum computers become practical, they could use Shor's algorithm to factors RSA gate, rendering RSAs insecure. So this is why researchers are developing post-quantum algorithms as future alternatives. And the last is slower than modern symmetric cryptography or bulk data. Algorithms like AES are much faster and more efficient for encrypting large volumes of data. RSA, because of its complex math and long key lengths, performs poorly when used for full data encryption. That's why in practice, RSA is often just used to encrypt the symmetric key, not the actual data.
RSA is still one of the most important tools in modern cryptography. It's trusted for tasks like secure key exchange and digital authentication. Because of its strong math foundation, RSA is widely used in things like website security, digital certificates, and email encryption. As new technologies like quantum computing emerge, RSA might not be strong enough on its own in the future. That's why researchers are already working on new, stronger cryptographic tools. But RSA can be slow. That's why it's often used together with faster algorithms. For example, RSA is used to encrypt a short secret key, and that key is then used by faster systems like IES to encrypt the actual data. This method is called hybrid encryption. It gives you both security and speed. Understanding RSA is essential for not only because of its history, but also because it lays down the foundation for many modern cryptographic protocols.
And that's a wrap on the RSA algorithm, the digital bodyguard we never knew we needed. Until next time, keep your messages secure and your prime even harder to factors. Thank you for watching.